Swayam Prabha. Digital India. Educated India.
Now, last time we talked about the formula for permeability, linear permeability as well as radial. So now there is an experiment. It's basically this experiment. Yeah, I take the red one. So this is called. I hope I can write it here now. Okay. This is called constant head experiment. What happened here is I'm just showing you the picture and then I will go to the whiteboard to explain it. Otherwise, I have to draw this picture. See, this is more or less replica of what test you are going to do in the lab. So there are basically 3 inlet we normally keep. One can make more than 3. We can make more than 3. Now, let's say these 2 are closed. Let's say these 2 are closed, and the water height is kept here. So water inlet is from here. So the water head, this is a simple pipe of about 75 millimeter diameter. This is more or less standard 75 mm, and we make these 3 inlet, but when we use only one at a time. Now let's say we are using the bottom one, so we know the height, and in the bottom we keep this a stone piece holder, so it is fixed at the end, and then this sample L, this is the sample length. It may be whatever the material we want to test the hydraulic conductivity. So it may be soil, it may be sand, it may be coarse grain, any conglomerate, it may be anything. But this testing we normally do for loose material. Okay, this is normally we do for loose, like soil type material. So let's say the length is L, and this water head is H, and water head is H. Okay, and now what happened? We have to maintain this height, this water height. We have to maintain this water height. So the inlet will be continuously coming, and the outlet also, the water will come from this side, from the bottom. Okay. So that has to be balanced so that the height H at no point of time during experiment is compromised. The H remains the same. That's why it's called constant head experiment. Constant head. Okay, that H remains constant. Okay, you remember that. So now under this pressure head, we have a length L, which is the sample length. So it's very simple. We can now write the formula, just Darcy's law. And that Darcy's law is this. Q is the quantity for a given time, which is came out, and we have measured it. K is the hydraulic conductivity, and you see it is exactly that formula. H is that water head. That means that was HA minus HB. Here HB is considered to be 0 because it's atmosphere. And this is basically LB minus LA. Okay, or that is the length L. So once we know this, why we are doing these 3 different cases? Because we vary the water head H so that quantity will change. So if H is high, Q will be high. So under that condition, we get at least 3 points like this. So we vary with age, the quantity changes. Then we draw a line, and the slope of this line, you can see the slope of this line is basically this K. The slope of this line is basically K. Okay, because you can see this is y equals to mx, and this is m, and this is x. So that is what we are plotting here. Okay. Another experiment is called falling head method. And this falling head is, let me first show you the diagram. This is in the book, you can see. So what is this showing is the porous material will be here, okay, in a kind of a chamber, and there will be some drain holes so that the water can come out. Here they say the name is falling head. That means we are allowing the head to change. In the previous experiment, we did not allow head to change. So the water inlet is equals to the water outlet. So it's a basically completely steady state flow. That means whatever is coming in, that is coming out. Here what is happening, let's say there is an initial water head, and we know the cross-sectional area of this. That's called standpipe, and that is, let's say the cross-sectional area is AP. And water is coming through that, and this will directly enter into it, and then water will come out through this. Okay, water will come out through this. So somehow it is not, this one is not working. And now, since the head is going to change, so what is the equivalence here? The equivalence is, let me come down. See, the quantity must be the same, right? Whatever it is falling through that standpipe, that smaller pipe, and that quantity is what? The dH by dt. Let's say for certain time dt, it has fallen by dH. So how much it has fallen? The volume, AP into dH is its volume, divided by dt is the rate at which it has fallen within that time, and that must be equals to whatever the Darcy's law told us through that cross-sectional area. So this is the A cross-sectional area of this sample. Then this is the L, the length of the sample. And so we know K into HA by L. This is from the Darcy's law. And this is what is the falling head. So now if we integrate between time T1 to T2, so you have to get two time, and you have to measure two heads, say starting head and the ending head at that time T2. So we get a formula like this. By integrating this, we can calculate the value K. Now, these are the two ways to calculate the hydraulic head. I will encourage you to think any other way if you can find out. This will be fantastic. Now we in our lab, we have the experimental setup for both of them. And when you come back, you will do the experiment of both of them in the setup, and you will find out the value K of that certain soil or sand. This is what will be asked you will be asked to do. Okay, so the formula and all these things I'm not writing, but you can get it from the book also. So this is what is the two experimental setup for finding out the hydraulic conductivity. All right. Now I will go and so I hope you are now seeing the whiteboard. So what I told you today is two experiments. What happened here? Okay. Number one is constant head. And number two is falling head. Okay. For finding out hydraulic conductivity. Okay. Okay. Now we will go to a territory where, let me draw it first, then I will ask you to calculate. Let's say this is a linear flow happening. Oh, sorry. And flow is going from here to here. And let's say this is some H, let's say A, this is some HB. This is the pressure head. The flow is Q. And this is total length is L, but each length is L1, L2, and so on up to Ln. And this has different rock layers. Okay, they're all different. So they have K1, K2, and all the Kn. So these are known. K1, K2, Kn is known. Okay. Quantity Q is flowing from A point to B point, where the pressure difference is, or the pressure is HA and HB. Definitely HA is greater than HB. Now, if I have to replace this by a equivalent material, let's say K equivalent, the same Q will come here and same will come out here. The length is again L. So you have to tell me, or I'm giving you 2 minutes to find out K equivalent is equals to what? This is a series combination of strata. Each strata having length Li and its hydraulic conductivity is Ki. Is that clear? So their length is Li and hydraulic conductivity Ki. They are under the pressure difference of HA minus HB for the total length L. So what will be the equivalent hydraulic conductivity of this combination of layers? You have done, the resistance equivalence if it is in series. Now it is the hydraulic conductivity equivalence. Calculate, and I give you, not calculate, you find out the equation. I'm giving you just 2 minutes, or somebody tell me how to do it, where to start. Anybody there?
So we can start using Darcy's equation.
Yeah, that's you have to use, but uh, what it is? That's his equation for each layer, right? Okay, you tell me for the first layer, what will be the Darcy's equation? This layer. What will be the Darcy?
Q is K1 HA minus HA
Something.
divided by
Okay.
L1.
Okay. So let me write, let's say del H1. This is the pressure drop, let's say I assume from here to here. This will be equals to Q by A using that Darcy's law. I am writing L1 by K1. Can I write that? Everybody see that?
Yes, sir.
Okay, I just rearranged. Okay. So basically it is the pressure drop for each layer is different. So this I can put I for ith layer, it will be like this. U and A is constant here because cross-sectional area here is constant. This is the cross-sectional area, and let's say this is constant for each layer. Now, definitely the sum of all this for all I equals to 1 to n layer must be equals to the same pressure drop. If I sum all this pressure drop, this will be the HA minus HB, isn't it? The total pressure drop. You know, you have done. Here is the pressure drop. Over there, you have done the voltage difference between the 2 points. Okay. So, or the potential difference, whatever. Here is the potential is the pressure. It's exactly the same thing. And so this one will be, again, I can write Q by A, because this remains constant, total L, or let me write summation of Li by K equivalent, right? So from there, you can find out that K equivalent is equals to these cancel outs. So I can write what I will write, summation of Li by summation of Li by Ki. Okay, that is your K equivalent here. Everybody got that?
Yes, sir.
Okay, so if the layers are in series, so and the same Q is flowing through all the layers, then we can find the equivalent hydraulic conductivity. Now, can you find the same for radial flow? I can give you the drawing of the radial flow, and let's say this is the well. Now I have different layers. Okay, of, let's say this is R1 and this is, or this is Rn, and let's say this is R1. This may be Hn and this may be H1. Let's say H1 or H0. I made it 0, then it is better. Can you find that out? And all these things have different. So this one is K1, K2, so on, K3, and up to let's say Kn. Here is the radius, is the difference. So can you find that out for radial flow? I hope you remember the equation. Otherwise, I can show you the equation. I think it is there. This is the equation. Okay. You can use this equation to build the equivalence. You write this equation, K equals to Q by 2 pi L. Here L remain constant, okay? And ln Ra, which is the extreme side, by Rb, and Ha minus Hv. The approach is same, okay? The approach is exactly the same. There is no difference between the approach. There is no difference between the approach. Only thing, you have to use that equation. And let me give you the formula so that you can try it in your home. So K equivalent is equals to ln Rn by R naught by summation ln Ri by Ri minus 1 divided by Ki. Okay. This is what will be the formula if you derive it. Okay, exactly the same way you can derive. Rn is the last radius or the largest radius where you have the maximum pressure. Okay, the maximum head. Okay, you want to try it or I go further? If you like to try, you can try it also. Naito, you try this. I give you another one. You try this thing now at home and derive it without looking at the book, okay, by yourself. Now let's assume, again, I'm in the linear flow, and this time the strata are parallel. Now, how is the parallel? The stratas are like this. So let's say this is K1, K2, and this is Kn. Q is flowing like this. And this Q is coming like this. L is constant for them. And this is HA and HB. So can now anybody tell me what is this K equivalent? You calculate that. This is a parallel combination. You can see that. Okay. So this is the layer number 1. And this is layer number 2. And this may be layer number 3 or layer number n. Now, what is the difference? Here, difference is in this. Okay. So this may be, let's say, I give in the book what I gave. Just a minute. The symbol so that you do not get confused. I gave T. So let's say these are T. So this is T1, matlab thickness. This is T2 and this is Tn. Somebody tell me what will be the K equivalent.
The area will be same.
No, here area is getting changed, na? That is on T. Is depending on T. This is the catch here. Your potential difference remain constant. You know, when in the series, your potential, that is the head potential, was different in different layer. Now here potential is same, just like electricity. In a parallel, potential remains the same. Okay, but here the difference is in that area, and that is controlled by T. So you just tell me now. It's very easy. For the first layer, you tell me what is the variable here? The area, right? You sum that up. Area is different. Q is different. What is the difference here? This is the total Q. So the Q will be divided now, right? So you tell me what is Q1? What is the formula of Q1? K T1. Let's say this width is somehow W. If you want to take, yeah, somebody is telling me something. His voice didn't come through though. So it's basically K1. This is that area A del H by L, right? This is the Q1. So you put now I for each layer, it will be same. Now if you sum this all, this is Q. And in equivalence, this one will be same. So that time it will be your K equivalent into summation of Ti into W. And this will give me the total area. Del H remains the same by L. So here this cancels. So now W is also cancels because W is the width. So the equivalent. So the equivalent, what do you get? K equivalent, if I have to just rearrange this equation, so this will be, where did I go? Here, summation of Ki Ti by summation of Ti. Okay, it's a basically just thickness weighted average. Okay, that is will be the equivalence. So here the Q get distributed just like current. Okay, over there current get distributed, here the quantity get distributed, and here we are following the Darcy's law. There you have followed the Ohm's law. That is the only difference here. Now interestingly, if you do the same thing for radial, let me just draw it for you, and I will again ask you to do it at your home, the radial thing. So the layer will be something like this. Then another layer, then another layer. The layer is like that, and my hole is here. So this is the H, let's say some A, and this is HB here. So flow is coming like this, but at different layer there will be different flow. Okay, because this one will have K1 and this will have Kn. So the depending on this hydraulic conductivity, the flow will be different. Okay. Similarly, here what is happening? This just if you say T, they are getting changed. Okay, and this is Tn. So this is what is changed here. And so as the Q, the total Q is going to change. Is not going to change, is going to distribute into the different layer based on its hydraulic conductivity. But remember that in parallel, the potential difference, the potential, here the potential meaning the head potential difference remains constant for each layer. Okay, just like Ohm's law. Because you know Ohm's law, just follow that. And here also the formula is exactly the same as the above. You can derive. Okay, so I hope you understood the concept of combining the layers. Now, sometimes there may be the layers, rock layers are not like so nicely, distributed, because you see the difference between the mining field or a geofield with any other engineering side is these are all mother nature, and the way they have formed, we have to take it. See, over there, if you, let's say in electrical engineering, some resistance is not working, you can change it. But here, if certain layer is not giving you any Q, you cannot change that. You have to just live with it. Okay. So we have to find out how to make the, let's say, petroleum or gas or water to flow through that layer. So we do fracturing and all these things to increase. And also the layer will not be deposited so nicely the way I have drawn. They may be in an angle, and that may be in a 3D angle. There are a lot of complicacy in actual field, and that need to be handled either with like this kind of equation we have to derive for that particular case, or there are some other sophisticated method you will know later on. So my point is, these are the 4 cases what I have told you. These are the basic cases. Linear series, linear parallel, radial series, radial parallel. Okay. So these are the 4 basic cases. Based on that, we have to build different models or different cases. Okay. Now we will do some problem. I start the beginning of the what I told from the last classes. This is exercise number 2.7. Let me make it little bigger, maybe for you to see. You can see that 2.7. Consider a cylindrical oil reservoir of radius 1.2 kilometer and height 20 meter, having in situ pressure of 45 MPa. Okay, by the way, do you understand what is in situ? Anybody? In situ stress? Is it?
Yes, sir.
Professor Barma has told you.
Natural stresses.
What is it? In situ? Like I have
So
written in situ pressure.
the natural stresses underground in the underground.
Yeah. So this is basically pre-existing. Natural meaning here, pre-existing. Before a human being or any other natural way, it has been disturbed. Before that, like mining disturbed the stresses, or stresses already existing in the in situ. In situ means the actual dictionary meaning is in place, whatever in place. Okay. So here the problem says the in situ pressure of 45 MPa. This is a petroleum problem. A well of 200 millimeter is drilled in the middle of the reservoir to extract the oil. Estimate the quantity of oil that may flow per day to that well. Assume the viscosity of the oil is 75 cp. Cp is centipoise. Okay, that may come a little later. And specific gravity of 0.85, permeability 50 millidarcy in situ condition. Okay. The assumed thing will come later. First, you calculate the conductivity. What is the oil conductivity here? Then we will change it to permeability and all this stuff. So what it is given here? The cylindrical oil reservoir of radius 1.2 kilometer. Okay. And the height is 20 meter. So your L is given 20 meter and RA is given 1.2 kilometer. You got that? And in situ pressure of 45. That means pressure difference is 45 already given. Okay. So how do you find out the conductivity? Oh. So the Q is, this Q is using that formula. Okay. 2 pi L K into HA minus HB ln RA by RB. Okay. Other than this one, other than K, we already know everything. See, this is given 20 meter. This is 45 HA minus HB. Now I am multiplying with 10 power 6 because I am converting into Pascal from megapascal. And this is converted into millimeter. Okay, this is 1.2 kilometer and this is just 200 millimeter. So converted into this. Now remains is the value of K because we need hydraulic conductivity. Sorry, here is the oil conductivity. Now oil conductivity will come from, because the permeability is given 50 millidarcy. So since permeability is given to us, so I gave you last time a equation, small k is equals to capital K gamma y mu, and mu is given 75 cp. So these are all conversion factors. By using this has to come into meter per second. See, this is given in millidarcy. Okay. Now 50 millidarcy converted into SI unit. If you see the book, this is the conversion factor. And this is converted into your gram per cc, or I think kilonewton per meter cube. And then this is the 75 is given as the CP. And I told you this 1 CP is 1 Pascal, 0.1 Pascal second. So all this thing, when conversion factor is used, it comes out to be this. So this is multiplied here. And this is given 3.566 megameter cube per second. So that was the speed, quantity at which this was flowing. Okay. Now this is a very elementary thing, but I would tell you the petroleum engineers, they do this. Okay, day in and day out, because this is what is the formula, Darcy's law, and that is their bread and butter. You can tell, you can know this. Now regarding the constant head, let me see whether we have any problem given. Here falling head is given. Now you just see the way the problem comes. Okay, This is very important. How the problem is being given to you. Okay. Let's say the following data are obtained from a falling at test of a soil. So we have done testing of hydraulic conductivity of a soil sample of length 13.4 centimeter. That is our L. So you remember this length L is 13.4 centimeter. Okay. Now how many readings we have taken? Now we have taken 4 readings. And you see the minute elapsed. So this is, I think, from a real test. Okay. That's why it is a real data. So at the 0 minute means when we have started the experiment, then the water level was 135 centimeter from some datum. Okay. From one datum, I think that datum was at the bottom. So that was 135 centimeter. Okay. Let me show you where is that datum so that you understand. So see, this is the datum. There was the initial water level. Okay. From there we are measuring. Okay. So that is 135. Then after 409 minutes, so how many hours? About 60. So maybe less than 6.5 hours. So after about 6.5 hours or so, the water level drops to 115 centimeter. So you understand the experiment because in your BTP or something, maybe you have to also do this experiment. For some soil you have collected from some mine and you need to do this experiment. So how we will do? So initial was H1, which is 135. Then after 6.5 hours, you came back and you saw this water level has dropped down. Okay, at certain level, which is 115. Like this, you have to collect the data. So 4 data has been collected. So you can see this is probably over a day. The data has been collected. Now the diameter of the standpipe, that means that small pipe is 4.4 centimeter and of the sample was 7.6 centimeter. So this is basically the real data. Okay. Now they are asking calculate the hydraulic conductivity of that soil. How much is the hydraulic conductivity? Okay. So now you completely understand that you have done a falling head experiment. So equation is known to me. This is the equation K equals to this. Or you can reverse way can find that out. If you write this ln h1 by h2 is equals to, you multiply by this. So T2 minus T1 is my variable here. So ln h1 by h2 is my y and k into this and rest everything is constant. Okay. So that is what we are calculating here. ln hj by hi, that means that h1 by h2 we are doing it. That has been calculated and this value has been calculated. So now if you plot y versus x, that is what we have plotted. So we got 3 points. Okay, we got 3 points. And the slope of this point of this line, the best fit line, is my k. And that is found to be 2.91 into 10 to the power minus 5 centimeter per second. So you see how slow it is. 10 to the power minus 5 centimeter per second. So it was hardly moving this water. So I think this is kind of a very maybe fine grained soil. That's why the value is low. Even we get even lower than this value also. If you do the testing in the rock, this will be even lower than that value. Okay, in the order of 10 to the power minus 6 also we get, so which is very low. Now the reason why I am saying this, you are going to become engineer, so you must have an idea of the numbers. If somebody asks you what is the general permeability or the hydraulic conductivity value of soil, so you should not scratch your head. Okay, you should be immediately tell, sir, in the order of 10 to the power minus 5 to minus 6 centimeter per second. Okay, it is in that low. Okay, but if it is a loose soil, maybe it will be much faster rate. And now you think about the groundwater, which is flowing below this earth surface, but through the rock layers. Now you can see this order is also more or less this, maybe 10 to the power minus 4 centimeter per second. So if you multiply by 3600, which is per hour, what will be that? Per hour, right? So you can find out per hour from point A to point B how much it has moved. Okay, what is the distance? So this is per second. You can convert per hour or per day. So normally hydraulic conductivity of a groundwater reservoir we normally give per day, and sometime you will be surprised to know, sometime in some rock layers it moves hardly a few centimeter in a day. So if the water is here beneath your house, next day it will move maybe 5 centimeter only. Okay, there are also rock layer like this. It is just not moving. And then if the water is not moving, what do? You have to increase the hydraulic conductivity. There is no other way, because pressure difference you cannot change. This is already I told you, this is Mother Earth. So whatever the datum, height and all these things are fixed. So only thing we can change is the hydraulic conductivity, and that by fracturing the rock or some other purpose we do. Okay. So now next time if the water is not coming in your house, from the groundwater, let's say in a tube well or something, you will probably know what is the reason for this. It is the hydraulic conductivity which is causing the problem. Okay, because pressure difference we cannot change. It is not a pipe that I make it little bit inclined and make the pressure difference more. This part I have omitted from the book. This is a testing in the real life, in the real field. Okay, let's see whether I have some in here or. So this is a very standard equivalent hydraulic conductivity problem, that find the equivalent hydraulic conductivity of 4 beds in a series having equal formation length for a radial system. So I think this you can try at home. I will go to the exercise if we have here. Let me see. I have the exercise problem also. Can you do number 5? Let me see. I have much more on number 5. Okay, you write it down. This number 5 problem, one data is missing though. A sandstone specimen having weight 320 gram has a diameter 54 mm and a height 60 mm. And the moisture content is 20%, having grain specific gravity 2.65. Find the porosity of the sandstone sample. Let me write you the data. The moist soil having W 320 gram, diameter is given 54 mm, length is given 60 mm, small w, there is the water content is 20% and GS is 2.65. Find P. This is the problem. What will be the porosity? Who can do that? You are seeing this? What I have written?
Zero 0.27.
Hmm?
0.27.
0.27. Anybody else got? So it is that
0.2.
equation you will use. 1
0.27.
minus. Okay, very good. So this GS into gamma W. Okay, this is that formula. Just everything is given. This is given. This is given. This is given. This you have to find out. Now only this is not directly given. So you have to calculate capital W by pi d square by 4 into L. Okay, that is the volume. So only thing you keep the unit okay, then it will be. So 0.27 means 27% is the porosity for this. This is the one of the way to find out the porosity. Remember that. This is just not a problem you have solved. I will give you a sample. When you come to the lab, I will give you a sample. You have to measure this diameter, measure the length, measure the W, that whether it is 20% or whatever, you will measure it. The GS only will be given to you. And this weight also you have to measure. I will ask you to find out the porosity. Okay. So this is by experiment. You have to find that out. Okay. So this is the formula you must know to find out. Okay. So this ends basically there are a lot of exercise problems. I think the TA will also, they will also take care of it next time.